Anyway, we're talking about stack machines. Today I want to talk about sort of stack machines as they relate to NFAs and DFAs, which we mentioned a little bit last time, and then also stack machines related to grammars. Can you convert back and forth between any of these categories of things? Some things are possible, not everything is possible. I thought maybe we'd start off with one last example. Last time was basically all examples of stack machines. I want to do just one more, which is a little more sophisticated, probably the most sophisticated of the ones that we've done so far. I would like to talk about the language of all x's on a B star such that the number of a's is equal to the number of b's. Number of a's equals number of b's. All right, this is like a to the n, b to the n, but it's more complicated because the letters can be in whatever order you like. A to the n, b to the n has all the a's at the beginning, followed by all the b's at the end. But this is just any mixture of letters in any order, but the total number of a's is the total number equals the total number of b's. Now, we have, my idea is, we have the stack to work with, and the stack can kind of remember things as you go through the string. As we saw with the language of brackets, the stack can sort of remember how many open brackets you've seen and then cancel them off accordingly. And I want to do a similar kind of a thing here. The number of a's equals the number of b's. The basic idea is, as you go down the string, the stack should remember how many a's you saw, and then sort of cancel them out every time you see a B. That's kind of my basic idea. So store, I would say store on the stack the number of A's as we read them. And then as you read a B, you cancel out one of the A's that you stored on the stack. And so by the time you get to the end, it should all be totally canceled out, and you'll end up with an empty stack, which is what you want. So store on the stack the number of A's as we read them, and then cancel on the stack when we read B's, all right? And then by the time you get to the end, if it was true the number of A's equals the number of B's, then you'll end up with nothing on the stack, which is what we want to be accepted in a stack machine. This is the general idea. There is one big problem with this approach. Anybody see a problem with this? The idea is every time you read an A, you add something onto the stack. I'll call it an X because I usually call it an X. And then every time you read a B, you cancel an X off of the stack. What's the problem with that?
Something like A, B, B, A. The second B wouldn't be able to push off whatever the A put on.
Yeah, right. The problem is you might see like more B's first before you saw the A's, and then you won't be able to cancel, like, because there won't be something on the stack to cancel. So this works. The basic strategy I outlined there, it works when you sort of see most of the A's first, and then you can cancel them off with B's later. But if you ever see B's before A's, then that's going to be a problem. So unfortunately, we have to make this slightly more complicated. I'm going to have two separate things that I put on the stack. One, I'll call them X and Y. X means I have extra A's so far, and this is how many I have. And then Y's means I have extra B's so far, and this is how many I have. And then you cancel them off accordingly. So really, we need to store sort of X for extra A's, and I'll call it Y for extra B's. So if it does happen that I read B's before A's, I store those as a Y, and then I cancel a Y with an A. And if I read A's before B's, I store that as an X, and I cancel an X with a B. It's a little confusing. I don't know. Not so bad. All right. I thought maybe I would just show a derivation. So before we write the rules, I'll just show sort of how I intend for this to work. And actually, this is a decent way, if you're trying to create a stack machine that does a certain thing, sometimes it's helpful to actually write out a derivation before you decide to write down exactly what the rules are. So the idea is, for example, I'll try and make up a long and interesting string here. if I have that string, this one does have an equal number of A's and B's. It has 4 of each. So this one should be accepted. And my strategy is I'm going to begin, since I see A first, that gets stored on the stack as an X. So my first step will read the A at the beginning, everything else here, and then put an X on the stack. Remember, we modify the stack on its left side. The left side is the top of the stack. All right, so since I read an A, that's sort of like one extra A so far, and I store that as an X. Now I see a B, and a B cancels the X, which means we're equal after the next step. So this B here, I'm going to read the next B. BBA, BAA is left over, and then I cancel the X, which was on the stack, and I end up with just S now. So when you see just S, that means at this point we're even. I've seen an even number, an equal number of A's and B's so far. All right, the next thing I see is a B. Now I can't, there's no X on the stack to cancel it with. This is sort of like an extra B. That goes onto the stack as a Y. So next it's going to say BA, BAA, YS. Now I see another B. This will go onto the stack as another Y. All right. A, B, A, A, Y, YS. Now I see an A. The Y on the stack means I had extra B's, so this A will cancel a Y. The idea is A cancels a Y, a B cancels an X. So this is now BAA, YS. I see another B which adds another Y, AA, Y, YS. And now these two A's will cancel those two Y's in 2 steps. So this will be A, YS, and epsilon S. And then I'm just going to have, my stack machine is just going to have a special rule that says you can clear a S off the stack for nothing. There you go. So this is how the thing is supposed to work. I hope that the idea is clear. It's not exactly an obvious idea. I mean, it's a little complicated, but we can handle that. All right, let's see if we can write down the rules then. What exactly are the rules that I was using throughout this procedure? So I would describe them, there's sort of 4 basic rules. If you see an A, you can cancel a Y. If you see a B, you can cancel an X. If you see an A and there already is an X, you add another X. If you see a B and there already is a Y, you add another Y. This is the basic idea. So I'm going to try and write what I just said. You always have the read, pop, push. This is how we do it. And the first thing I said was, actually there are 2 sort of technicality ones. If I read an A and there's an S on the top of the stack, that means like this is what you do just at the very beginning when you're getting started. You push XS onto the stack. That's actually what I did in the very first step here. There was an S, I replaced with XS. All right. Okay, and then there's a similar thing. If you read a B at the very beginning, which that didn't happen. Actually, it happened right here. There was an S on the stack. It was replaced by YS. All right. Usually, though, the rules are something like an A cancels a Y and a B cancels an X. So I'll try and write that. If you read an A and there's a Y on the stack, you cancel it entirely, which is to say you push epsilon. And if you read a B and there's an X on the stack, you cancel that. So you push an epsilon. What if I also need rules for read A and X and read B and Y? Remember, X represents like I have an extra A. If you had an extra A, that's what this means. If you read an A and you had an extra A, you should make it. Now I have 2 extra A's. That's the idea behind that line. And similarly, BY, Y means I had an extra B. If I read another B, now I have yet another extra B. So it's like that. All right. And then finally, just this is basically it, but I did have one special rule right here where I just canceled the S at the very end. That is just going to be epsilon S epsilon. So that one you only use at the end, but it's just to clear the S off of the stack at the very last moment. All right? Yeah?
Why do we need a pop off the X? and then push 2, or could we just pop them up and then push 1?
I think that would be the same.
Oh, okay.
Yeah, maybe that's a little clearer. For some reason, the examples in our book, they don't do it exactly this way, but they don't like to pop epsilon in our book. They would rather do it in this way. Actually, maybe that, I think actually there's a reason in this example to do it like this. If you said, so this is he's suggesting instead of that, why don't just do this? And I agree the net effect is to insert another x. So you could say remove an x and then add in 2 more is the same as just not removing anything and adding only 1. The problem with that is you could screw yourself by using this rule if there's already a y on the stack. If there's already a y on the stack and you read a, you should cancel the y. But if you instead do this rule, you will add an x in front of the y, which messes everything up. So really, it's because if you put an epsilon here, then that means you can do this rule whenever you want, which is sometimes a bad idea. You only want to do this rule when there's already x on the stack. So this is a better way of writing it, I think. All right, great. I thought just as a little warm up to make sure everybody's with it. Can you show using these rules here? Let's give a derivation showing that ABBABA is accepted. All right. See what you think. I'll give you a moment to try it out. You can talk to your friends if you like. So, I mean, a derivation in the style that I wrote, like at the top there, that kind of stuff. You should begin with ABBABA, comma, S, and then do the rules one at a time. If you like, you can give them numbers. You want to get down eventually to epsilon, comma, epsilon. That's a satisfying, thrilling conclusion. It's gonna be fine. I'll try and write my answer up here. All right, I think I did it. And as I was going around, it looked like everybody else pretty much was doing it just fine. Really, if you're doing it properly, there really isn't much choice about what you should do next. You just gotta, find the proper rule to apply in each step. I suppose at any point you can do rule number 7, although you shouldn't do it until the very end. You'll just mess it up if you try to do rule number 7 earlier. I hope you got something like this. Anybody got any questions about this? Excellent. I think writing the derivations is really not so difficult. Creating a stack machine is actually, in my opinion, quite tricky to get the right idea and formulate it in terms that that you can write down as a stack machine. But lucky for us, actually, it is fairly easy to create stack machines by converting from other types of things. And that's what I want to talk about for the rest of our time today, probably. If you ask me, actually, sort of, if you meet me in the club and ask me to write a stack machine for something, probably the way I will do it is by first writing an NFA or a grammar and then converting it to a stack machine, because I find that to be a lot easier than trying to create the rules by hand. So I want to talk about converting sort of NFA / grammar to stack machines and vice versa. All right. To me, this is actually an easier way to create a stack machine, and I'm pretty much always going to try to do it this way by converting from a grammar or NFA. Now, this is not always possible, so we need to talk about exactly when is this strategy going to work. Last time I already described in kind of vague terms. I want to describe a little bit more specifically this time. We talked about how NFA can always be converted easily to a stack machine. So converting NFA to a stack machine is easy. You just have to know sort of the trick, but it's once you know how to do it, it's quite simple. So the idea is, if I have, I'll just do an example. Here's my starting state S. Give a name to every state in your NFA. I am just making an example here. Some of the states will be accepting. There might be epsilon transitions. No problem. All right. This is a NFA. Give a name to all the states, and the idea is we use the states as stack symbols. So on the stack, you're going to see letters like S, T, Q, and R. And you use the stack just to keep track of which state you're in. So I begin with the stack saying S. If you read a A, you should change the stack so that instead of S, it now says T. If you read a B from there, you should change it so that instead of T, it now says Q. So you use the states as stack symbols. I'm going to say one at a time. That is to say, when you're doing a NFA, actually it is never necessary to pile up more than one thing on the stack at a time, because all the stack needs to do is remember what state you're in as you're going through the letters. So use the states as stack symbols, one at a time. And then each time you follow an arrow, when we follow an arrow, change the stack. So in this example, I would have something like read, pop, push. S goes to T. You can basically just transform or translate each arrow in the diagram becomes a rule in the stack machine. And S goes to T says, if I read A and pop S, that is to say, if you already are in state S, which means the S is in the stack, and you read A, what should happen is you go to state T. That is to say, you want to see T on the stack. So it's like that. If you read A you can replace a S with a T. That's what I meant by saying, when we follow an arrow, change the stack. So if you're in state S and you see A, you should change it to state T. And this is how you do that on a stack machine. And then we just translate all of the other rules accordingly. So I have an arrow, an A arrow from S to Q. So I can also read A, pop S, push Q. I don't know if you asked yourself earlier, am I allowed to put 2 lines in a stack machine with the same read pop? The answer is yes. As we've already seen, what with epsilon lines and such, there are cases in a stack machine where you have some choice of which rules to use next. And so this is an example where I have 2 different rules which apply in the same situation, and it's your choice which one you want to use, just like in the original NFA diagram. All right, anyway, those are the only rules involving pop S. What about T? I have one arrow T to Q, so that needs to say B, T, Q, right? That's the arrow going from T to Q labeled with a B. I have an arrow from Q to R with an epsilon. That will be an epsilon read, Q to R. And then I have an arrow R to T. That is a read A, pop R, push T. All right. And this is basically it. There is something, so I've translated all the arrows. You should also make sure that you have properly accounted for which one is the starting state and also which ones are the accepting states. So the starting state is S. That is accounted for down here just because I use S as my starting stack symbol. So you don't really have to do anything special for the starting state. We should talk about the accepting state. Actually, nothing in this list here indicates that R is an accepting state. Anybody have an idea? How could we make it so that R is an accepting state? Basically, you want it to be so that when you're doing your stack computation, if you read the whole string, you get all the way down to epsilon in the string part. I'm thinking of those like pairs. If you get all the way down to the epsilon in the string part, and the other part is just R, then it should be accepted. How could I make that happen? Yeah.
You want to read epsilon, pop R, push epsilon.
Yeah, right. You want one rule that you can use when you're done, basically, like this. Read epsilon, pop R, push epsilon. That means when you're done, you can clear R off the stack and be finished. So this last line right here, this is encoding. So these ones, I would say, these are the arrows. And this is the fact that R is an accepting state. Right. If you have more than one accepting state, then you put more than one line like that at the bottom. All right. Just to convince ourselves that this really works, can we try a derivation? Let's see. Let's derive AB on this machine. All right. Now, because I have an epsilon transition, and I also have, like, as I said, the first 2 lines here are can both be applied to the same situation. So there is some trickery involved in making this derivation. You have to make sure that you are choosing the correct rules to apply from one step to another. So what's my strategy? Your strategy should be, when it comes to deciding which rule am I supposed to use first, like I see A first, should I do the first line or the second line? How to decide this is, I would say, look at the diagram first, look at the NFA, and figure out how is it that AB is actually accepted here. And then do those steps in that same order. So when I want to decide which steps to use to derive AB, first I look at the NFA diagram here, and I try to decide what is the path through the diagram which makes AB accepted. Can anybody say? It's not that hard to say. Yeah, what do you think?
The first one?
The
Where
first.
you read A, pop S, push T?
Yeah, right. In the diagram, the way to make AB accepted is sort of that way, right? I want to do those arrows in that order. So on the stack machine, I use those rules in that order. That's the idea. So I go ABS, and this becomes doing the arrow across the top first. I go read A, pop S, push T. So now it's B, T. Then I do the diagonal arrow next. which is a read B, pop T, push Q. So this is going to become epsilon Q. And then I do the epsilon arrow across the bottom, which is read epsilon, pop Q, push R. So this becomes epsilon R. And then R is an accepting state, so I got to do the last rule there, which clears the R. Epsilon, epsilon. Ha hey. It's kind of satisfying, in my opinion, to get down to the epsilon, comma, epsilon, and you feel good about yourself. It's like when you're in high school, you wrote mathematical proofs which end with a line that says 0 equals 0, and you're like, yes, 0 equals 0. It's not a good way to write a real mathematical proof, by the way. I already know 0 equals 0. You don't have to prove that 0 equals 0. You should have written your proof differently. Anyway, that's the idea. Can I just say very, very sort of explicitly here? So generally speaking, something like, if you see this on the diagram, this becomes read A, pop X, push Y, right? And then any accepting state, if it was something like X was accepting, this becomes read epsilon, pop X, push epsilon. And that's really all there is to it. So it's a simple procedure. I suppose you have to sort of memorize exactly how it's done, but it's not a big deal. All right. You can have some practice with this on the homework. There are no surprises, though. It really never gets any harder than the example that I just did. Something to note, so this is just, what this means is any NFA can be converted to a stack machine. And this is, I think, something that I said last time. Sorry to scroll so fast. So any NFA can be converted to a stack machine. And that means that any regular language can be the regular language of a stack machine. It can be the language of a stack machine, right? That's, if you're thinking about what kinds of languages can you do on a stack machine, it includes every regular language plus some others, right? We've already seen like A to the N, B to the N you can do on a stack machine. So I'm going to say, so any regular language, that is to say the languages of the NFAs, can be computed by stack machine. All right, the stack machines can do any regular language. They can also do more because they can do things like A to the N, B to the N. All right, that is the relationship between stack machines and NFAs. It's pretty simple in my opinion. What about grammars? We got another 20 minutes. I think we can talk about grammars. What about grammars? Grammars? Oh, sorry. I meant to say, can I just say one more thing? I think I said something like this, but just to make it explicit here. Not every stack machine can be converted back to an NFA. Not every stack machine can be converted to NFA. That's because we already have seen examples of stack machines with non-regular languages, like for A to the N, B to the N. There is a stack machine for that, but we already know that's not a regular language, so there cannot be an NFA for that. So that means there is no possible general procedure that will convert back the other way. All right? Okay, what about grammars? These are sort of two things. Can we do, a stack to a grammar? Can we do a grammar to a stack? These are two separate questions, I suppose, and I want to talk about both of them. I would like to talk about the second one first. So, can you convert a grammar into a stack machine? And then also, can you convert a stack machine back to a grammar. Let's talk about this one, and we'll talk about the other one next time maybe. Can I convert a grammar to a stack machine? It is a true fact. Actually, you can do this. So we can, not any grammar, but we can convert any context-free grammar to a stack machine. It is necessary that it be context-free, and we'll talk a little bit about that eventually, but I want to talk about the procedure. Again, this is a fairly easy procedure, although you just have to see how it works and remember how to do it. But once you know how to do it, it's pretty easy to do. For example, I want to just do something like, here is a sample context-free grammar. I'm going to try to make it somewhat complicated here. All right. S goes to A, B, S, A, or T, and then T goes to B, T. So the way that I think of this, it's not really important, but basically the first step here, S goes to A, B, S, A, is making some kind of balancing thing with A, B on the front, matching with A on the end. So this will create strings that look like A, B to the N, with an A matched with an A to the N on the end. And then what ends up in the middle is you do this as many times as you like to create the outer two ends. And then in the middle you create a T, and it says T goes to BT. So what you end up with in the middle is just a bunch of B's. I'll say to the M, where that M is a different number than N. I mean, it might be different. All right, so that's what the language is, but that's really not, it's not so important that you know that's what the language is. Let's try to make a specific derivation just because I want to speak very particularly about how this grammar works. Let's derive, how about A, B, A, B, 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 A, A. All right, so how that would look, what I see here is A, B on the front, sort of balanced with AA on the end, and then some extra B's in the middle. So I'm going to do the first rule through twice, because I want to get two copies of the AB on the front and two A's on the end. So I'm going to go, S goes to ABSA, and then once more, AB, ABSA, A. All right, that was the first grammar rule twice. And then I'm going to go, this S in the middle needs to become those three B's. And the way to do that by grammar steps is first S becomes T, and then I go T goes to BT 3 times. So first I go S goes to T, A, B, T, A. And then I go T goes to BT 3 times. So this is A, B, BT, A. That was once. A, B, BT, A. That was twice. And then one more. A, B, T, A. And then finally T goes to epsilon. A, B, A. And that's what I want. All right, so this was a derivation using the grammar. I hope everybody remembers what grammars do for you. My goal is to convert this to a stack machine. Like I said, it's a simple procedure, although it's a little weird and not at all clear how that it actually is going to work. But I will describe to you how to do it first, and then we'll try and talk about why this actually works. So anyway, in our stack machine, the stack alphabet will be the S and the T. This may be not a surprise. What kinds of things go on the stack? They are the S and the T, but also I'm going to, from time to time, put A's and B's in the stack too. So in this example, the stack alphabet is going to be A, B, S, and T. All right, and of course the stack can also be the empty string, but that doesn't count as an alphabet letter. So we will mostly have S's and T's on the stack, but also it's going to be important to allow little a's and little b's on the stack too. All right? And here's how you do the translation. Each grammar arrow, remember those are called the productions. Each grammar production becomes an epsilon read. And it looks just like the arrow does. So S goes to ABSA, becomes epsilon S ABSA. This is read, pop, push. Sorry for the page break there, PDF readers. All right. A grammar line like that just translates directly into a stack line like that. So each grammar production becomes an epsilon transition, and then we also allow transitions like A epsilon, B epsilon. I shouldn't say allow, we need them. They're not just allowed. We also use not only tolerated but celebrated, right? We also have transitions like this. If you read A from the string and see A on the stack, you can pop it and just throw it away. All right? Let's try that same example grammar and convert this into a stack machine in the way that I said. Now, like I said, it is not immediately obvious at all that this is going to work, but have a little faith in me. It really does work. I want to try and convince you of that by doing an example. So this becomes, actually there's going to be quite a few rules here, but I got read, pop, push. All right, so what I said was each grammar arrow becomes an epsilon read. So the first one, S goes to ABSA, is epsilon S ABSA. The next one, S goes to T. You read that first line there as if it was like two separate things. S goes to ABSA is one thing. S goes to T is another thing. That looks like epsilon S T. And then I have the two more, right? T goes to BT. That becomes epsilon T BT. And then T goes to epsilon. Becomes epsilon T epsilon. All right? So those are the production rules. And then we have special rules like this, which is the other type of rule that I said. All right, so these ones here are the productions. And these ones here are what I will call something like read pop letters. If you have an individual letter on the stack and you're also reading that same letter, you can throw them away. That's the, those are those two rules. If I was working with A, B's, and C's, I would also put C in that list of rules at the end. All right. Can we see if we can do a derivation on the stack machine of the same string? So let's derive that same string I had before. A, B, A, B, 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 A, A. All right. Let's do this derivation on the stack machine. The way to do this on the stack machine is, here's my, my pro tip. Follow the same grammar steps in the same order. Red is for pro tips. Follow the same grammar steps in the same order. So when I want to derive this using the stack machine, of course, since almost all of my stack rules are epsilon transitions, you have many choices in each step of what you're going to do next. How do you decide what to do next? You think about what did I do in the grammar derivation and do that same stuff in the same order. So can I just extend my pro tip here? Follow the same grammar steps in the same order and pop letters when possible. You'll see what I mean by that in a moment. All right, anyway, we begin. A, B, A, B, 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 A, A, and S. Maybe I'll give numbers to these just so that we are all with it. This is a little confusing the first time you do it. The stack derivation is going to be kind of long. I mean, my grammar derivation was kind of long also. But I think we can do this in 10 minutes. It's not hard, really. You just have to keep it straight what you're doing. So what shall I do first? I have S on the stack, so really there's two choices. I could do rule number 1 or rule number 2. I'm going to do rule number 1 because, if you recall, when I was doing the grammar, I did the first grammar step. In fact, I did the first grammar step twice. All right, so I'm going to basically do rule number 1 twice. So I begin by doing rule number 1 here. And so this is an epsilon read. So actually the big string stays big like it is. Do not change the string. A comma. But the stack changes. Instead of S, which it is now ABSA. All right, that was rule number 1. Now, I said I wanted to do rule number 1 twice, but actually you can't do rule number 1 again in this situation because rule number 1 involves a pop S, and the S is not on the top of the stack. I am going to do 5 and 6. This is what I meant by saying follow the same grammar steps in the same order. Pop letters when possible. I have an A here and an A here. I'm going to do rule 5 to pop away those two matching letters. So rule 5 will clear out the A at the beginning of the string and also clear out the A at the front of the stack, like so. All right. And I can do another read a B, pop a B. Right? I have B at the beginning of the string and B at the beginning of the stack. So now I'm going to do rule number 6. This is another letter pop operation. It becomes now A, B, 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 A, comma, S, A, like so. All right. And now I am finally ready to do rule number 1 again. My goal was to begin by doing rule number 1 twice. Could I just say, can we take a moment to appreciate what's going on here? We created, so the S here turned into ABSA, and then I was able to cancel AB off the front of the string. And now I have, the way that the stack works is kind of working sort of as, kind of opposite to the way the grammar works. The grammar works by starting with S and nothing else and building the string out of nothing, all right? The stack machine is actually going to work sort of in the other way. It is by starting with the entire string and gradually eating up the letters until you end up with nothing at the end. And what we've done so far is I did step 1 once, which created A's and B's at the beginning, which I was then able to eat away from the original string. Now this string kind of has an extra A at the end, but that's going to be accounted for by the extra A at the end of the stack, so everything's going to be great. Anyway, let's do rule number 1 again, because that was my next actual grammar step to do. So this is an epsilon read. Sorry, I've scrolled, but I can remember what it said. S becomes ABSA, so that S becomes now ABSA. And then there was an A already on the stack, so the stack now says that. ABSAA. All right? And now I can pop letters again. I have A on the front of the input and also the front of the stack, so those A's can go away. That's rule number 5. B, 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 A, A, B, S, A, A. And then I'm also going to pop away the B there. That's rule number 6. It now says B, 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 A, A, S, A, A. All right? Now we are again at the point where we have to decide what rule to use next, and I am going to be inspired by the grammar steps that I used. So if I scroll back up to my grammar derivation, I did, so in the first step it was basically grammar step number 1, and then I did that again. I did this one twice. The next step was changing the S to a T, so that's S goes to T. That's the stack step that I'm going to do next, which is rule number 2. So I go 2 is read epsilon, pop S, push T. So this, by rule number 2, there were other choices I could have done in this step, but I'm going to do number 2 because I know that's the one that works out in the grammar. TAA. All right? And then, again, inspired by what I did in the grammar next, I did t goes to bt 3 times in the grammar next. And so I'm going to do that. That is rule number 3, epsilon t bt. So I'm going to do number 3. Come on now. Number 3, it's going to be, this is an epsilon read, so the string stays the same. T goes to BT, means now BTAA. And now I can do a read B, pop a B. That's how it is on these streets. I read a B, I pop a B. I don't know what that means. All right, BBAA, TAA. Now I'm ready to do another grammar step. I did T goes to BT 3 times. Remember, I've just did once in my stack derivation, so I'm going to have to do that 2 more times. That's rule number 3. T goes to BT, so this is BBAA, BTAA. Again, rule 6 will cancel B's, BAA, TAA. And then finally, one more time with the rule 3, T goes to BT. So it's now BAA, BTAA. And then another 6, I clear the B's. AA, TAA. I'm feeling good about this. All right, I have A's left in the input, 2 A's left in the input. They are going to naturally cancel with the 2 A's that I see on the stack. The next grammar step that I did at this point in my grammar derivation, I'm kind of here. I have just done T goes to BT 3 times. And then I go T goes to the empty string, and we'll be done. So that should be rule number 4. T becomes the empty string. A, right? And now I just do read A, pop A twice. That's rule number 5, and it'll be over. Read A, pop A gets me AA. One more time, gets me epsilon, epsilon, which is finally accepted. All right. It's a long stack derivation, but you are basically following the same grammar steps. This actually, to me, is if you demanded of me that I create a stack machine for this or that, this is probably how I would do it. I find it easiest to first make a grammar, which is like the homework problems do for tomorrow, and then convert that to a stack machine in this way. All right. Any questions or thoughts about that? I think it's about time to go, so maybe I'll just leave it at that then.
Is stack machine